Hello guys, welcome to H2O, the A to Z of chemistry. I am Dr. Ritu Johar, your educator for this course, the periodic table. Today we will begin with lecture 17 from the course, but make sure you have watched the previous ones before viewing this one. So in the periodic trends of properties of elements, we are discussing electronegativity. In that we've covered what is electronegativity, what are the scales for measuring electronegativity. Then in the last lecture we discussed what are the factors affecting electronegativity and the trends in the periodic table. So we will be completing the topic of electronegativity in this lecture, wherein we will be discussing the applications of electronegativity. So the first application of the electronegativity concept is to determine the polar character of covalent bonds. So in electronegativity, what is the bond we are considering? We are considering a covalently bonded molecule because we are understanding the tendency of an atom to attract the shared pair of electron. So the shared pair of electron forms a covalent bond. Now we discussed in the first lecture of electronegativity that the molecule formed by a covalent bond, it can be a non-polar molecule, it can be a polar molecule. Non-polar molecule, for example, we discussed hydrogen molecule where it was a covalent bond formed between the two similar hydrogen atoms and the electronegativity difference between both of them being zero. Then the other example we took was HF. So HF, it was formed between two dissimilar elements. They had an electronegativity difference between them. Fluorine was more electronegative, hydrogen was less electronegative. Fluorine had a partial negative charge, hydrogen had a partial positive charge, and hence it was a polar molecule, right? So now you can understand that the electronegativity difference is what is causing a polarity in the covalent bond. So more is the electronegativity difference between the bonded atoms of a covalent bond, more polar is going to be the bond. And if the electronegativity difference is greater than 1.7, the bond formed is generally an ionic bond, whereas if it is less than 1.7, then it is going to be a covalent bond. And the percentage ionic character of a bond, this depends upon the electronegativity value according to this formula. 16 into delta chi plus 3.5 into delta chi square. This will give us the percentage ionic character. Okay. And also do remember that the molecules like H2, N2, Cl2, where the electronegativity difference is going to be zero, they are going to be non-polar molecules. So the second application of the electronegativity concept is going to be the prediction of the acidic nature. Now what is an acid first of all? Well, from the definitions that you have already done in your junior classes, though you will be learning more definitions how to define an acid later on this in class 11th itself. The definition of an acid is that it is one which furnishes H ions in the aqueous solution. So whenever we are adding the acid to water, it is going to release H ions. For example, you studied about HCl, H2SO4, HNO3. So all of them, they dissociate to form H ions. And for example, HCl it is, so H ions plus Cl negative ions, H2SO4, so H ions and sulfate ions. Now, this is what is first of all an acid. Now, how do we explain the acidic nature on the electronegativity concept? Remember that only the bond that is going to break will be where the electronegativity difference is maximum. Okay. So what you do is take the example of H2SO4. So this is the structure of H2SO4 in which we have three elements: hydrogen, oxygen and sulfur. Now see the electronegativity of hydrogen, oxygen and sulfur. H is having electronegativity value 2.1, oxygen 3.5 and sulfur 2.5. See the electronegativity difference between oxygen and hydrogen. and oxygen and sulfur. So oxygen and hydrogen, it is going to be 3.5 minus 2.1, so it is 1.4, and sulfur is going to, oxygen and sulfur is 3.5 minus 2.5, so it is 1. So this means that the electronegativity difference between hydrogen and oxygen, which is 1.4, this is greater than oxygen sulfur, which is 1, right? So now what I told you is break the bond where the electronegativity difference is maximum. So we will break which bond? We will break this bond. Okay, so the moment this bond breaks, it is going to release what? It is going to release H ions. So hence, wherever the electronegativity difference is maximum, we are going to break that bond, and from that we are going to understand whether the considered compound is acidic or not. Okay, so I hope this is clear. So the next application of electronegativity will for the prediction of the basic nature. What is a base? Well, that is the one which furnishes OH ions in the aqueous solutions. Again, the tendency to donate OH ions we will explain on the basis of electronegativity difference, where you have to remember that the bond that is going to break in the molecule will be the one where the electronegativity difference is more. Okay, so we have NaOH as an example. The bond is between Na and O and a bond between O and H. Check the electronegativity difference. For oxygen and hydrogen, we get the electronegativity difference to be 1.4. For oxygen and sodium, it is 2.6. So if the electronegativity difference of O and Na is more than O and H, where is the bond that is going to break? This is the bond which is going to break. Okay, so when this is the bond which breaks, what is being released out? It is going to be the OH ions. And if OH ions are being donated, this is going to be a base. Okay. Next, we can also predict the nature of hydroxides again on the same concept. Just check the electronegativity differences and break the bond which has maximum electronegativity difference. So we have a hydroxide AOH. There can be two cases. One is that the H ion is OH bond is breaking and H ions are being released, and the other is that AO bond is being broken and the OH ions are released. So when H ions are released, it is an acid. When OH ions are released, that is going to be a base. So we can say from here that if the electronegativity difference between O and H is more than O and A, it is going to be a acidic hydroxide. And if the electronegativity difference of O and A, okay, is more than O and H, it is going to be a basic hydroxide. For example, we have ClOH and LiOH. Just check the electronegativity difference. We have chlorine oxygen electronegativity difference being less than oxygen hydrogen. So this is the bond which will break, and therefore OH is going to be a acidic hydroxide. Whereas if you compare lithium and oxygen, the electronegativity difference will be more than OH difference. So this is going to be a basic hydroxide, right? So I hope this is clear to you people. Now what do we conclude from this? We conclude that the metallic hydroxides, they are basic, and the non-metallic hydroxides, they are acidic, right? And down the group, remember that the basic nature of the hydroxide increases. Okay. And a longer period, the acidic nature of the hydroxides increase. So just like the nature of hydroxides, we have the nature of oxides as well. The oxides, they can be neutral, they can be amphoteric, they can be acidic or basic. So what you have to remember is that the acidic oxides, they are the ones which are non-metallic in nature, right? So N2O5 is an acidic oxide. Basic oxides are the ones which are metallic in nature. Okay, so the metal and the oxygen, they combine to form a basic oxide. A non-metal and oxygen is forming a acidic oxide. We have certain exceptions over here. CO, NO, N2O, they are neutral in nature, and we have BeO, ZnO, copper oxide, Al2O3, SnO, SnO2, PbO and PbO2, which are amphoteric oxides. And please do remember them. They are very frequently asked in the examination. So the trick is going to be that you have to remember that all of the non-metallic oxides, they will be acidic. All of the metallic oxides, they will be basic, but the exceptions of neutral and amphoteric oxides are these ones. Okay, so please do remember this. So down the group, the basic nature of the oxide is going to increase, and a longer period, the acidic nature of the oxides increases. For example, if you see the period 3 elements, we have Na2O, MgO, Al2O3, SiO2, P2O5, SO3 and Cl2O7. So what we are saying is that the acidic nature of the oxide is increasing in a period from basic to acidic, right? So metallic oxide to non-metallic oxides, we are moving from a basic to a acidic oxide nature. Similarly, you can see for the period 2 elements, we have lithium oxide, beryllium oxide, B2O3, CO2 and N2O5. So basic to acidic nature. Okay, so you have to remember this. This is very important, that a longer period, the acidic nature of the oxides increases. Down the period, the basic nature of the oxide is increasing, and these are the neutral and the amphoteric oxides that you have to remember. Next application of electronegativity would be in the checking of the acidic strength of the hydrides. First of all, what are hydrides? Hydrides are the compounds between any element and hydrogen. For example, we have HF, HCl, HBr, HI. Okay, we have CH4, NH3, water, HF. All of these are hydrides. Okay, so now when we have to check the acidic strength of hydrides, what do we mean? We want to see which of these acids is going to release an H ion more easily, right? Now, when we consider the strength of the hydrides in a group, first of all, you have to remember that if we take the electronegativity values, maximum difference is going to between HF, and down the group the electronegativity values, they decrease, right? So according to that, you would say HF is the strongest acid. But no, you have to remember that down the group the electronegativity values, they do not change to much an appreciable level. Okay, so the important factor for determining the acidic strength of the hydrides down the group is not going to be electronegativity, but it is going to be the size of the halogens over here for this example, right? So fluorine, this has a smaller size than chlorine, and iodine, you can say this has the maximum size. Okay, so now what happens is when the size of iodine, this increases, so the shared pair of electron, this is farther away from the nucleus of iodine, so hence a lesser force of attraction towards the nucleus, weaker is this bond. So the bond between H and I, this is going to break much easily than the bond between H and F. Hence, as this bond is weak, so the acidic strength of HI is going to be the maximum. So acidic strength is going to increase down the group due to decrease in the bond strength. When we consider a period, in a period, yes, there is an appreciable change in the electronegativity values. Over here, comparing with the atomic size, we take what values? We take electronegativity values, right? So now the electronegativity values, they are going to be more important. So we will be seeing the maximum electronegativity difference. So maximum electronegativity difference is going to be for HF, least is going to be for CH bond in CH4. So the acidic strength will increase across a period because of increase in electronegativity values. So you can remember this for always. This is very important. Otherwise, you are going to confuse and commit mistakes that the properties of the elements are compared on the basis of size of the atom in a group, whereas the properties are compared on the basis of electronegativity or charge along a period. Okay, so please do remember this. This is going to be very important for you. Next, I have a few questions just to have a rough idea of what all we have been talking about. These electronegativity values that we discussed, please remember they are all just indicative. They are not exact values. So please just do not be going along a hard and fast rule that this is the value that is coming. So this should be. Okay. So these are just going to give us an indication. The values in the question is the values of electronegativity for carbon, hydrogen, sulfur and potassium. They are given to be 2.5, 2.1, 2.5, 0.8 respectively. And you have to classify the following bonds as probably ionic polar covalent or non-polar covalent on the basis of electronegativity values. So you can understand the word probably. So this is just going to give us an idea whether according to these values the bond can be of what type. So the bonds which we have to tell which are going to be polar ionic or not is HS in H2S, CS in CS2 and KH in potassium hydride. So now if we see the HS bond in H2S, the electronegativity difference is going to be 0.4. So this difference of 0.4, this is quite small. So we can say that the HS bond, this is going to be slightly polar covalent. Had it been 0, we would have said it is non-polar. But because it is 0.4, we say that this is slightly polar covalent. Next we have CS bond in CS2. Now the electronegativity difference between carbon and sulfur, this is 2.5 and 2.5. So this is 0. So if this is 0, what are we going to say? That the bond is non-polar. Next we have the KH bond. Okay. So the KH bond, the electronegativity difference is coming up to 1.3. So we say that the bond is polar covalent with about 40% ionic character. The next question we have is we have to calculate the percentage ionic character in HF. So this we will be doing according to the formula. Percentage ionic character is equal to 16 into delta chi plus 3.5 into delta chi square. And if we know the HF electronegativity values, we will be able to do this quickly. But remember that these values, they are just going to give us a fair rough indication of the percentage ionic character and not the exact values. So chi F minus chi H, this is equal to 4.0 minus 2.1 and this is going to be the electronegativity difference as 1.9. So now you will put these values of 1.9 to calculate the percentage ionic character and you will get the value as 43.035%. Okay. Next, we have to calculate the electronegativity difference between two atoms if the ionic character in their bond is 19.5%. So the equation you already know now. Just put the values, solve the quadratic, and you will get the delta chi values to be -1 or 5.5. Right? So again, I'm telling you, so these are just the approximate values that you get. When we have the maximum electronegativity value of fluorine to be just 4, this value cannot come as 5.5, but this is coming. So these are just an approximate ideas to just have an idea, nothing more than that. So that would be all for this lecture. I hope the applications of electronegativity, they are clear to you. Still, if you have any doubt, please feel free to mail us at h2ochemistry@gmail.com. You can also put your query in the comment section. And well, if you've liked the lecture, please do click on the like link. Also do subscribe to our channel if you've not done till now. And then you have to just click on the bell icon to get a notification as and when we put up a new lecture for you, a new course for you. So we will be meeting again for the next lecture, which is going to be on atomic volume, right? Atomic volume, and one more thing we will be discussing here is the valency. So I hope you will join me back for the next lecture. So bye bye and have a nice time. Enjoy your studies.